Hello everyone. In today's class we will discuss the CTL model checking algorithm. In last few classes we have discussed the CTL syntax and semantics, and also we have taken one class where we discuss various example how do you encode certain property in CTL. But at the end of the day, when you write the property, you need to check that property in a cryptostructure or transition system, right? And we need to also understand the algorithm that checks a property on a system, and that is what the basic intuition we will discuss in today's class. Just to recap, you have given a property which is in CTL phi. You have given a model which is a cryptic structure which is a set of states, say a relation transition systems, the leveling, every node has some atomic proposition leveled, and S0 is the start state. So what is our problem? Given this transition system M and given this formula phi, I have to check the start states, all the paths starting from the start state satisfy this formula or not, right? And the answer of this algorithm should be yes, if all paths starting from S0 satisfy this formula, or no when there is some path on which this formula does not satisfy, right? So that is the problem statement we have, and this transition systems we understand, right? Transition system, and the CTL formula can have atomic propositions, the Boolean connectives, temporal operators, and the path quantifier, and this we have discussed in detail. I am not going to further discuss, right? So this is what I have already discussed, that the algorithm will take a formula over this and then input the formula as well as the model and just check whether that satisfy or not. Okay. So this is the overall things we have to do. Now there are two ways we can do this. One is basically you try to identify whether this state S0, the start state, satisfy this phi or not, right? So effectively you identify all paths starting from this start state, and you, in this all path you check whether the formula holds or not, right? So that's can be the strategy one. The other strategy, which is basically based on a leveling algorithm, where we are not checking only from S0, rather we try to level the states with the formula, and we will check what are the states where this given formula phi holds, right? And then if S0 among those states, then I will say that this particular model satisfy the formula, right? I am repeating again. The approach one is where I am starting from only S0 and taking all paths, right? And I will check whether the phi holds on those paths or not. So this is the strategy one. The strategy two, instead of only starting from S0, I will identify the set of states where this formula holds, phi holds. And if S0 is among them, then I will say this particular model satisfy this formula. And this is the second approach is basically better. Here I can do the same thing using level propagation. So I am not going to do the exact precise path identifications and check whether the formula holds in that path or not. Rather, I will try to propagate the levels starting from some start states, and then I will see whether the states where which can be labeled with phi. Okay, and that algorithm is more efficient. So this is the approach we are going to follow in our model checking algorithm. Okay. So now the given a bigger formula, okay. So before going to that, the algorithm further, we have already discussed in the previous class the adequate set. So we have already seen that there are 8 combinations, right? AX, EX, then AF, EF, right? AG and EG, and AU and EU, right? So there are 8 possible temporal combinations, but we have already identified this is the adequate sets. If I can find algorithm for this only these 3, that would be sufficient, right? And for Boolean it is a negation and an or, right? So we will identify that formula for this, and if something is written in other things like say AX, the formula has other term like say AU, AG and all, we will convert them into this using equivalent expressions, right? So we are only bothered to algorithm which based on this. So, how this leveling algorithm works in general? So, if the formula has other operator like this A, U, E, G and all, we will convert them into only using the adequate set. So, those conversion equivalence we have already discussed in the last class. Now, you might have given a very big formula like this, right? How do you approach? Because I am saying that I am going to level the states with formulas, right? How I will do? I will basically identify all the sub formula. So, for example, what are the sub formulas are here? You have P, you have Q, you have not P, right? Then you have A, not P until Q, right? Then you have A, you have P until A, not P until Q, right? And so on, right? Similarly, so if I write this is as say phi 1, this is phi 2, and then I will write I have formula phi which is effectively A, G, P implies phi 2, right? So, these are the sub formulas. So, what I will do? I will effectively start from the smaller sub formulas. I will see what are the nodes which level with P and Q, and what are the states where P it is not level with P, I will level with them not P, right. So, this is already done. Now, since these are done, now I can start leveling for A not P until Q. I will try to see what are the nodes where A P not until Q holds, right. I will talk about that in more detail. So, once this phi 1 is done, this is basically phi 1, right, this is basically your phi 1. So, then what I am going to check is, I am going to check whether A P until phi 1, right, if this is your phi 1, this is equivalent to this. So, I will try to see level the states with A P until phi 1. Once that is done, then I can take the entire formula and check, right. So, this is how the bottom up approach will have happened. So, I will identify all the sum formula and I will level the states with starting from the minimum one, right. So, I will grow, right. So, this is the overall approach. So, let us move to the leveling algorithm. So, as I mentioned that I have to level the states, right. So, if some node has already P level, then it is already, I know that that states P is true, right. So, that basically states has I level with P because that level is already there, right. Conjunction is very simple. If some states has already phi 1, the level it is already level with phi 1 and level with phi 2, then I will also say that states also satisfy phi 1 and phi 2, which is very obvious, right. In that state phi 1 holds, phi 1 may be some P, right, or it may be big formula, but say phi by some way I am able to show that phi 1 holds in this state, and this and phi 2 also, this state is also level with phi 2, then I will say I will level that state with phi 1 and phi 2. Similarly, for negations, if it is not level with phi 1, then I can say it is level with not phi, right. And as I mentioned, this process goes bottom up approach, right. I will basically start from the minimum formula and I will grow to the actual formula. So, this is understood. Now, the three operator I talked about AF, EU and EX, I will see how we can level for these three, right. So, then I know how to level the entire formulas, right. So, let us start with AF. So, AF means what? I have a state, I can say that AF phi holds in this state if for all path from this, right, there may be many paths from this in some future state phi true, right. If this is the scenario that from this state is 0, all paths are there, in all path in future phi holds. So, this is your intuition, you have to achieve that, but I am not going to explicitly identify the paths and I will check whether in some future state phi holds, then only I level that state with AF phi. I am not going to do that. What I am going to do is very interesting. So, what I will do, I will start leveling the node where phi holds, right. That node I will start with, I will also level with AF, okay. So, why? Because in some state where phi holds, then there also AF phi holds, right. Future includes the current state, right. So, you should remember that semantics of future, it is starting from there is some future state including the current state, right. So, I greater than equal to 1 in that definition, right. So it includes the current state. So any state where phi holds I can mark with AF. And then I am going to do this. So this is interesting. So I will try to identify a state, right, whose all immediate successor is already marked with AF. Okay. Then I will also mark that particular state with AF. Right. So what is happening here? So I already identify this, let us say phi holds here, phi holds here, phi holds here. So I have already marked that with AF phi, right? AF phi. This state also I have marked with AF phi. This state also I have marked with AF phi. Now I found a state whose all successors, right? All successor is marked with AF phi. Then I will mark this state also AF phi. Okay, and this way I will grow, and this I will repeat, right? I will try to do this every time, right? So basically I have only initially what will have a set of states where phi holds, they are AF phi holds, right? Then I will try to identify the states from where all transition is coming here, right? From where all transition is coming here to some of the states here. Then I will mark these states also as AF phi, right? And this process will continue, right? So my set is growing, right? So I will grow like this, and I will get a final set where all the states are marked with AF phi, and that is called least fixed point. So this is the minimum fixed point is possible because I am starting from minimum, I am growing, and this is the least fixed point. I do not want to go beyond that, right? So this is how I am going to mark the states with AF phi. So now all the states here belong to these sets where AF phi holds. So what is the definition of AF phi? That AF phi I already told that I will mark a state whose all future states. So that includes the current state. So if in some state where phi holds, I can also mark with AF phi, right? Now I found another state where whose all successors are marked with AF phi, right? So this is marked with AF phi. This is also marked with AF phi. Then I am marking this with AF phi. That means from this state at least I am a future state where AF phi holds, and if AF phi holds, it may be in some future of this phi holds somewhere. That is why this AF phi holds here. So I can also say that AF phi holds here, right? So this is kind of correct by construction, right? So I am making sure that any state which I am marking with AF phi, it guaranteed that there will be some future, in all path in future, there will be some state where phi holds, right? This is how I am constructing it, right? So this is my labeling algorithm for AF phi. Now if you understand this, other two will be very easy to understand. So now next I will do E phi 1 until phi 2, okay. If you remember the definition of E phi 1 until phi 2 is something, there exists some path in which every state phi 1 holds until I reach a state where phi 2 holds, and this future state includes the current state. So this can be the situation, or I have only here phi 2 holds, right? So then I will write, there may be multiple paths, but at least in path is happening, then I can write this E phi 1 until phi 2 holds here. Here also if phi 2 holds in that state, I can also write E phi 1 until phi 2 holds, right? So these are the two scenarios I have to achieve. So what can be my starting point? I can start with the states where phi 2 holds, because by definition they are E phi 1 phi 2 holds, right? So what I am going to do, I start with a scenario where all the states are phi 2 holds. I will also mark E phi 1 until phi 2 holds, because by definition E phi 1 phi 2 holds there, right? Now the labeling algorithm. What I have to see? I have to identify a states where phi 1 holds, and there is at least one next state where E phi 1 phi 2 holds, right? Then I can mark this state also E phi 1 and phi 2, right? So I will basically include those states here, right? So I will identify all the states where phi 1 holds, and there is at least one next state where E phi 1 phi 2 holds. I will include all such states, and I also mark them as E phi 1 and phi 2, because in this state phi 1 holds and there is a future state where E phi 1 phi 2 holds, means that will ensure that there will be some future state where phi 2 holds. So I can mark these states also E phi 1 and phi 2, right? So this process will continue, and again I will get a least fixed point, right? It will grow. So it will basically give you all the states where E phi 1 until phi 2 holds, right? So the leveling algorithm is understood. I start with the states where phi 2 holds, I will mark them as E phi 1 until phi 2 holds. Then I will identify the states where phi 1 holds, and at least one successor where it is already labeled with E phi 1 and phi 2. Then I will mark that particular state with E phi 1 and phi 2, and this I will continue until I cannot label a new state. Okay. So just to give a visual explanation, so here I have phi 2 holds, right? I have phi 2 holds here. Then I have marked this state with E phi 1 and phi 2. So this is my initialization. Now I found a state here where phi 1 holds, and there is one next state where this holds. Then I will also mark this state with E phi 1 until phi 2 holds, right? So here phi 1 holds, right? So this process will continue. So initially this is the only state where this holds, then I got this state, then there may be another state from where this is happening, then I will include that, and this way it will grow and get a fixed point, right? The next one is Ex phi, okay. So this is easy because it is only the next state, you do not need to apply repeatedly, there is no fixed point needed here, right. So how can I do that? It means that I am in a state and there is one next state where phi holds. So it is easy. So I will label all the states where phi holds, and then I will identify the states where whose at least one successor is where phi holds, then I will write it Ex phi, right. So here phi holds and I have a transition from this state. So in this state I will write Ex phi holds, right. So this is one time affair. So I will just do it once and I will stop, because it is not something Ex phi holds. So I will identify the next state from here, I will mark it Ex phi, right, because for Ex phi has to hold, not Ex phi, right. So I do not need to do the repeated fixed point calculation here. So it is basically one time computations. But this is how I can label all the states with Ex phi, this is how I can label all the state with E phi 1 and phi 2, and this is how I can label all the state with AF phi, right. And now whatever the formula, and this is I am starting from the minimum formula and I am going to the entire formula, and then I will say whether the start state is 0, where that actual original formula is labeled with that formula or not, right. If it is, then I will say this model satisfies this property, right. So this is the order approach. So let us look into the complexity, it is very important. So we will go one by one. Ex phi. So what I am doing here, I am identifying the states whose next state phi holds, right. So basically I have to go to each node and then I have to check his all his edges, right. From this node all the edges I have to check to find that successor, and in successor whether phi holds or not. So this process I have to effectively visit all nodes and all edges, right, to identify this Ex phi, right. Because for this node I visit this transition, there will be another node from I will visit his next states, there will be another state from where I will visit his next states, right. So effectively I am visiting all states and all the edges, right. So the complexity should be order of V plus E, right. So this is what written here. Now let us look into E phi 1 and phi 2. Here I can achieve also V plus E using backward VFS. So I will explain that. So let us now look into E phi 1 until phi 2. So here we have mentioned that we already know the states where phi 2 holds, in that state phi 1 until phi 2 holds. So this I can do by order of V, right. I can go to all the nodes and check whether phi 2 holds there, and I will mark them E1 phi 2. So this can be done in order of V, because I am effectively going to all nodes, right. I am assuming that V is the number of nodes and E is the number of edges in my transition system, because I am doing everything in terms of the in the transition system or the critical structure, right. Now what I am going to do? I am going to do backward VFS. That is interesting. If you do not do this, if you try to do the forward one, because what is the definition? Definition is I will mark the states where phi 1 holds, and I will try to identify one successor where this E phi 1 until phi 2 holds. So if I try to do it in a forward manner, so I will identify all the states of phi 1 holds, and then I will go to all successor, and then I will check is any of them is where E phi 1 until phi 2 holds, then I will mark this with E phi 1 and phi 2. Then what will happen in this forward manner? So I will identify all the nodes are phi 1s in order of V, then I have to effectively search all successor nodes to see whether there is at least one node where E phi 1 until phi 2 holds. So, it is effectively you are searching all edges, right, which is the kind of complexity will be V plus E, right, because all nodes plus all of their successors, and this is one step, and this will keep repeating, right. This is we are going to repeat maybe n times, because in every iteration maybe one node getting marked and next iteration another node will getting marked. So, the worst case the complexity will be order of V into V plus E if you do forward breadth first search, right, BFS. But if I do backward BFS, so then I don't need to do this V plus E every time. I will explain that, and that is very interesting to note, right. So, I start with the node where phi 2 holds, or rather E phi 1 phi 2 holds, and then I will only go backward, because from this node I can go to all its previous nodes. So, I am in a node like this, it can have 3 previous node, right, not successor, the previous node, and if that node has phi 1, I will mark that with E phi 1 until phi 2, right. I start with E phi 1 until phi 2, right. Now, here you see that I have visited this node and all these edges, and now I move to this node, right, because here also I marked. From here I will start and checking these edges, right, and then I go on, because this node I will not cover further, because here phi 1 does not hold. So, in this process what is happening, I am starting from one node, I go to one of the previous successor and I am going to these previous successors and so on. So, all the edges are visited at most once, not multiple times. So, here it is not V into V plus E, it is order of V plus E, right. So, if you do a backward VFS, you always get a better complexity, because you are not visiting the edges multiple times, you are visiting any edges at most once. But if you do forward, because you are in this node, you have to visit all of its successor to check whether E phi 1 until holds, then only I can mark this with this. So, effectively in one time I am visiting all edges, right. So, this is basically V plus E, all nodes and all their edges. So, it is V plus E, right. Now, this is just for one iteration marking this E phi 1 until phi 2, right. So, I mark this with E phi 1 until phi 2. Now, I have to do the same thing for other nodes. Again I have to do that for each nodes and each of their successor, right, because then only I can do this. So, searching the successor, each successor every time, right. So, that is why this V plus is happening into V times, right. So, the backward VFS give you better complexity, which is order of V plus V. This is backward BFS, right. So, if I do this backward VFS, I will get V plus E, but unfortunately this AF you cannot do backward way, okay. So, you have to get complexity order V into V plus E. So, let me explain that. So, in the B plus E, what is happening here, I have to check all successor, right. I cannot start with a node where AF phi is marked, because if I start from here, I can go to the one of the successor, but I have to check for this node all successor, right. I cannot just say if one of the successor where AF phi holds, here also AF phi holds. So, I have to start from this node and I have to do forward BFS, and I have already mentioned that if I start from a node and do forward BFS, so to identify one node where AF phi holds, it will take V plus E, and this process, because you are doing repeatedly, you have to do worst case for all nodes, and it will be V into V plus E. So, if you can avoid the forward VFS and you can manage the things doing backward VFS, your complexity will be less. But for AF phi you cannot do that, so your complexity will be high, V into V plus E. Okay. But in the next class I will show that instead of taking this as in the adequate set, I can replace this with EG, and for EG it is possible to calculate in order of V into V plus E. Okay. So, in next class I will give you the exact algorithm to compute this. In addition to that, I will discuss the efficient computation of EG in place of AF, and I will show that overall complexity of CTL model checking is actually order of V plus E into the formula, right, the formula size, it is F, because you are starting from each sub formulas, right. If the sum formula is big, you have to take the size of that F also. but one searching is V plus E, and this may depends on the size of the formula. So, the overall model checking complexity will be order of F into V plus E. So, this detailed algorithm I will discuss in the next class. Thank you.